Hi, everybody. Now I want to look at another example of a way to make cyclic groups. It's kind of just a different approach. It's another nice additional example to have on hand. It's based on the complex numbers, and so I'm going to start with a very fast review of a few facts about the complex numbers that you've probably seen before. So let's take it away. So complex numbers, which you can write as this fancy C, is a collection of numbers of the form a plus bi, where a and b are real numbers and I squared is minus 1. And you multiply and add these numbers as you would expect, as if they were polynomials, taking into account this relationship that I squared equals minus 1. I'm not going to belabor this. I'm going to assume that at some point in your life, you've worked a little bit with complex numbers. But I do want to remind you that we have a graphical picture of a complex number. We can think of a complex number as giving a point in the Cartesian plane with x, by convention, the real part, the x-axis is the real part and the y-axis is the imaginary part. And this gives an alternative way of writing the complex number because if you use the Pythagorean theorem, we have that the hypotenuse of this triangle is a squared plus b squared, which is often, if we call this complex number z, the norm of z squared is r squared. And so we have that b is r sine of theta, and a is r cosine of theta. And so our complex number z can also be written r cosine of theta plus I sine of theta. And there's a convention. If you've worked with complex exponentials before, then you know this is probably re to the I theta. If you haven't worked with complex exponentials, then we're just going to make a notation. We're going to follow the book. The book uses the term cis of theta to mean cosine theta plus I sine theta. It's a definition. So with that definition, our complex number can be written r cis theta. And what's nice about this is that if you if you have two complex numbers, z1 is r1 cis theta 1, and z2 is r2 cis theta 2, then z1 times z2, well, it's r1 r2 cis theta 1 cis theta 2. But we have a very nice property, which is that cis theta 1 cis theta 2 is the same as cis of theta 1 plus theta 2. So z1 z2 is r1 r2 cis theta 1 plus theta 2. Now, if you've worked with complex exponentials, this is just the statement that e to the I theta 1 times e to the I theta 2 is e to the I theta 1 plus theta 2, which is just the law of exponents. If you haven't worked with complex exponentials and you want to see why this is true and you're brave, what you can do is you can take cosine theta 1 plus I sine theta 1 and multiply it times cosine theta 2 plus I sine theta 2, and work this out, and you get something plus I times something else. And if you look at these somethings and use the addition law for sine and cosine, you can eventually figure out that this turns out to be the cosine of theta 1 plus theta 2, and this turns out to be the sine of theta 1 plus theta 2, and therefore you get this formula. So if you haven't ever done this in your life, it's worth doing, but I'm going to spare you the algebra and not work it out, and I'm just going to rely on this rule for multiplying complex numbers with the understanding that we have this picture, namely that if z1 is z is r cis theta, then r is the distance to the origin, it's the magnitude of the complex number, and theta is the angle with the x-axis. So if we are interested in just the complex numbers of norm 1, so these are all the complex numbers z of the form cis theta, where r, so to speak, is 1. These are all the complex numbers which lie on the unit circle, and they form a group because when you multiply, if z, we can check this in a number of ways. Maybe we could check the axioms directly. So first of all, the identity element 1, which is just cis of 0. So I'm going to let's let, I think the book calls it T, be the collection of complex numbers z such that z equals cis theta for some angle theta in the real numbers. And that's called the circle group. So 1 is cis of 0, so 1 is in the circle group, and we have to check that every element well, I won't check that the multiplication is associative. It's just multiplication of complex numbers. That's associative. And then we need to check on inverses, and for that we can use the fact that if z is cis of theta, then z inverse is cis of minus theta, since cis of theta, cis of minus theta is cis of theta plus minus theta, which is 0, which is 1. And of course, this group is also abelian because cis of theta times cis of tau is cis of theta plus tau, which is the same as cis of tau plus theta, which is the same as cis of tau, cis of theta. So this group is called the circle group because its points are the points of the circle, but you can you think of them as angles and you multiply them together by adding the angles, but taking into account the fact that if you go around the circle more than once, you come back to the place you started from. And this is actually an interesting group. You could think of it as the group of rotations of the circle, the symmetry group of the circle, and it's very definitely infinite because each of these angles gives you a different point. So it's quite a large group. But we're going to be interested actually only in some, at least for now, only in some of the elements of the circle group. And those are called the roots of unity. So they correspond to complex numbers z of k, where the angle is a fractional multiple of 2 pi. So just to sort of draw the picture, if we look at if we fix n to be, let's say, 4, then we're interested in z of k is by definition cis of 2k pi over 4, which is cis of k pi over 2. And so if k is 0, that's 1. If k is 1, that's cis of pi over 2. Cis of pi over 2 is the complex number which has an angle pi over 2. That's what we normally call I. So this is cis of pi over 2. Then there's negative 1, which is cis of 3. Sorry, this is k is 0, k is 1, so k is 2 is cis of pi. And then finally there's minus I, which is cis of 3 pi over 2. And you notice that even though I've defined z of k for any integer, in fact, if n is 4, then as k goes around, there's really only 4 different ones. And if k is 6, there's only 6 different ones, and so forth. So you can calculate with these z of k's, and I've sort of put a few properties here. The first one is that if you multiply them together, you add the indices. So let's just check the proof of the proposition. So first of all, we want to show that z of k, z of j is z of k plus j, but that's just the additive rule for cis, because this is cis of 2k pi over n times cis of 2j pi over n. And you multiply those together, and by the addition rule here, it's 2k plus j pi over n, which is z of k plus j. The second property says that if you take z of k and you raise it to the m, that's the same thing as taking z of m times k. That's really just a restatement of the earlier thing, because z of k to the m means z of k plus z of k m times, and that's the same thing by the previous result as z of km, because it's z of k plus k plus k plus k plus k, which is z of km. And then the last point says that two of these are equal. Well, it says, first of all, z of k is equal to 1 if and only if n divides k. And to see that, if you look at cis of 2k pi over n, this is equal to 1, well, only if this angle, 2k pi over n, is an integer multiple of 2 pi. Because the only time that in order for this angle to correspond to 0, you have to go around an integer number of times times 2 pi, and that's only going to happen if k over n is an integer. And k over n being an integer is the same thing as saying that k is a multiple of n, in other words, that n divides k. And if you take this result and combine all the things that we know, then you see that z of I and z of j are equal if and only if divide both sides by z of j, and you get z of I minus j equals 1. And by the previous result, that only happens if I minus j is a multiple of n, which is only if, that's by definition, I is congruent to j mod n. So there are, so these z of k's are closely related to the integers mod n, although they're not exactly the same. But z of I is the same as z of j if and only if I is congruent to j mod n. And these numbers are called the roots of unity because if you look at the polynomial z to the n equals 1, by the fundamental theorem of algebra, in the complex numbers, a polynomial of degree n has n solutions counted with multiplicity. And the n solutions to this polynomial are exactly the number z of I for I goes from 0 up to n minus 1. And it's easy to check that the z of I are solutions, because if you take z of I to the n, that's z of n times I. But n times I is certainly congruent to 0 mod n. So z of ni is certainly equal to 1. So if you raise any of these z of i's to the nth power, you get 1. On the other hand, we know that because the numbers 0, 1, dot, 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 up to n minus 1 are all distinct mod n, their differences are all less than n, so the differences can't be divisible by n. We know that z of 0, z of 1, all the way up to z of n minus 1 are different. And there's n of them. I guess this should be, sorry, it's not z of 1, but z of, no, this is, these are different, sorry. I got a little tangled up there. These are all different, and there are n of them. So they must be the n roots of these polynomials, and of this polynomial. And it's also true that if you multiply them together, I mean, z of I, so to show that they're a subgroup, we just need to check that z of I times z of minus j, which is z of I minus j, well, that's again in this group mu n, because the z of i's are all, or any I is in there. N is fixed throughout all of this. And finally, if we take z of 1 and we look at its powers, so z of 1 squared is z of 2, z of 1 cubed is z of 3, all the way out to z of 1 to the n, which is z of n, which is the same as z of 0, since n is congruent to 0 mod n. Again, we know these are all distinct. So what we've shown is that this collection, which I'm calling mu n, is a cyclic group of order n. Generated by z of 1. And more generally, among the z of 0, z of 1, these n things, so z of j is a generator, means that if we look at the equation z of j to the k equals 1, that means that n has to divide jk. Remember, we know that this is equal to z of jk, and that's equal to 1 only if n divides jk. And n divides jk if we let d, if and only if n over d divides k, where d is the greatest common divisor of n and j. So if the greatest common divisor of n and j is bigger than 1, then we could take k to be n over d, and that would be less than n, and so z would not have order n, because there would be a smaller power of z of j, which gives us 1. On the other hand, if the greatest common divisor is 1, then we see that the smallest power k for which z of j to the k is equal to 1 has to be n, and that means that z of j is a generator. So just to wrap that up, if d is bigger than 1, then z of j to the n over d is equal to 1, so z of j is not a generator. It's because the cyclic subgroup generated by z of j is not everything. It's only part of the thing, part of the collection of roots of unity. But if d equals 1, then z of j is a generator. Remember that the order of an element, we proved, is both the size of the cyclic group that it generates and the smallest power for which you get 1. So if the power for which z of j to the n over d gives you 1, then that means that the cyclic subgroup generated by z of j has a size at most n over d, which is smaller than n. On the other hand, if d is 1, then the smallest power such that z of j is 1 is n, and so it's the whole group. And just to give an example, if we take n equals 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's my attempt to draw a 12 gone. And so these would be the z. This would sort of be z of 0, which is 1, z of 1, z of 2, z of 3, z of 4, z of 5, z of 6, z of 7, z of 8, z of 9, z of 10, and z of 11. And the angles here would be 2 pi over 12, which is pi over 6, which is 30 degrees. So the interior angles of our not very well drawn 12 gon would be 30 degrees. And the vertices which correspond to generators are are z of j, with j relatively prime to 12, not having any factors in common with 12. And those are going to be j equals 1, not 2, not 3, not 4, 5, not 6, 7, not 8, not 9, not 10, 11. So 1, which is here, 5, which is here, 7, which is here, and 11, which is there. Those are the roots that correspond to generators of this cyclic group. And everything else, if you take powers of it, generates a smaller group. So the roots of unity that form generators are called primitive. So z of j is called a root of unity, a primitive root of unity, if it generates mu n. So there are, in the case of n equals 12, there are 4 primitive 12th roots of unity.